Solving probability problems involving forming a password with letters and digits. Let us recall the fundamental counting principle, which simply states that if there are m ways to do one thing and n ways to do the other thing, then there are m times n ways to do both things. Okay, let us now analyze this problem. A password is formed using 3 letters of the alphabet, excluding the letters A, E, I, O, and U, and using any 3 digits, excluding 0. The numbers and letters can be repeated. Now, I underlined the word "and," trying to call your attention on the fact that we are talking of 3 letters of the alphabet and any 3 digits. That means the 3 letters has to follow one another. That is, they should be consecutive. Then the 3 digits, again, they have to be consecutive. That is, one following the other. That is the meaning of the word "and." Now, we need to calculate the probability that a password chosen at random starts with the letter B and ends with the number 4. That is in A. In B, we need to calculate the probability that a password chosen at random is exactly 1B. C, we need to calculate the probability that a password chosen at random has at least 1 4. So I will explain as I give solution to each of the tasks we have from A to C. Now, before we give solution to the problem, we need to make some analysis and write the actual figures that we are supposed to work with in terms of the letters and the digits. We know that the alphabet has 26 letters, right? But we are told that we should use the letters excluding the 5 vowels, that is A, E, I, O, U. Then if we subtract 5 from 26, we have 21 letters. So we shall be working with the 21 letters of the alphabet. Then in terms of the digits, we know that in mathematics, we have 10 digits, right? 0 to 9. And any number we write down in mathematics will be making combinations of any of these 10 digits that we have in mathematics. So that if I say 25, 48, I'm making combinations of the digits we have from 0 to 9. But we are told that we should exclude the 0. Then we are starting from 1 to 9. Therefore, to know how many digits are there from 1 to 9, we use the counting without counting concept, that you say 9 minus 1, you get 8 plus 1, you get 9. So we have 9 digits that are between 1 and 9 inclusive. Right. Now, the fact that we want a password, 3 letters plus 3 digits. So it is a 6-length password, meaning we shall be working to fill up 6 positions, right? And also we need to note that repetitions are allowed. Okay, now, the fact that we want to calculate probabilities, first and foremost, you should understand that probability is a fraction between 0 and 1, and being that the numerator of that fraction represents the favorable outcomes, the denominator of that fraction represents the possible outcomes. Therefore, let us first find the possible arrangements, which we shall refer to as our possible outcomes, and we call that set S. That is, how many passwords can we come up with when we are making combinations of 3 letters and 3 digits. Since we have 6 slots to fill, therefore, these are the 6 positions that we have for the letters and digits. So I'm going to consider my first 3 consecutive positions to represent the letters. Therefore, the fact that we have 21 letters, that means on the first position, any of the 21 can occupy that. That means we have 21 choices. So position number 2, the fact that repetitions are allowed, that means any letter that was positioned on position 1 can also be put on position 2. So we still have 21 choices, 21 letters. The same can be said to the last position for the letters. We still have 21 because repetitions are allowed. Now I'm done with the letters. I go to the digits. I have 9 digits. That means the 4th position, we have 9 digits to choose from. Therefore, we have our position 4 with 9 choices. Since repetitions are allowed, this position again, we have 9, and the last one, we have 9. Therefore, if this is the case, that means by fundamental counting principle, since these numbers, as they are written, they are representing the choices in the 6 different positions. So together, we then apply the fundamental counting principle by multiplying 21 times 21 times 21 times 9 times 9 times 9, right? Which gives us, after writing it in index form, 21 to the power of 3 times 9 to the power of 3, you can reduce it to get this number. But as such, is acceptable that you can leave it as it is. Right now, we have our possible outcome set, right? So we then go to A to try to answer the question. We need to calculate the probability that a password chosen at random starts with the letter B and ends with the number 4. So as such, we need to come up with our favorable outcomes set. That is then the fact that obviously we are having 6 positions and the repetitions are allowed, but we need to attend to this condition of starting with a B and ending with a 4. Therefore, that set we are going to call it set F. So these are the 6 positions. First, we should have a B. Last, we should have a 4. That is what is being said. So now we have the other 4 slots to place the letters and the digits. But the fact that now the B is fixed here, then we are saying B is there, 4 is there. Fine, but repetitions are allowed. So the B can also be found here or elsewhere. Even the 4 can also be found anywhere. But otherwise, by putting a 4, we know that every other codes, the passwords we are going to come up with, the B will be the first and the 4 will be the last. Therefore, to fill this position, we still have, that is second position for the letters, we still have 21 letters to fill this position. Then after this is done, still repetition allowed, we still have another 21 letters. Then we are through with the letters, we go to the digits, right? This position, we still have the 9 digits to occupy. The same can be said on the other number position. So the repetitions allowed, we are respecting here, independent that we have placed the B and a 4 there. We can still have B also occupying these other 2 slots. The same can be said for a 4. Right, now, once we have done that, by the fundamental counting principle, we are saying the number of favorable is you multiply the individual choices we have at different positions. That is 1 times 21 times 21 times 9 times 9 times 1, which is what I have here. Then this reduces to this figure. Now that I have my favorable outcomes, then what I need now is to actually calculate the probability that a password chosen at random starts with the letter B and ends with the number 4. So as such, we are saying the numerator occupied by the number of favorable outcomes, the denominator number of possible outcomes. The favorable is what you have seen here. The possible outcomes is what you have seen here. Then this reduces to 1 over 189. Now, if you write this number as a decimal fraction, you see that it is nearer to 0 than it is to 1. Remembering that probability is a number between 0 and 1. So when it's nearer to 0, we are simply saying we have a slim chance of coming up with the passwords starting with the letter B and ending with the number 4. That is the meaning of this probability. Okay, we go on now to B, calculate the probability that a password chosen at random is exactly 1B. Of course, I've carried forward the number of possible outcomes, right? So for us now to find that probability, we need to find favorable outcomes. That is, passwords have exactly 1B. And we call that set F, right? So again, we have this situation where the green shall be occupied by letters, the blue by the digits. But I'm saying the fact that we are only going to have 1B, if the B is right at the first position, then that means I don't expect to have a B here, neither here. And what does that mean? It means of the 21 letters that we are working with, we have removed the B's no longer there, right? So this second position, I'm left with 20 letters, right? Once I fill this, the fact that repetitions are allowed, again, this third position, I'll also distribute the 20 letters, right? For the numbers, there is no restriction. It will be 9, 9, through and through. So this is the situation. One for the B, we remove it from the letters, then we are left with the 20. This position, n of the 20, and repetitions are allowed. Then again, the last position for the letters, n of the 20. Then the 999 for the digits, right? This is a possible arrangement. We can have another arrangement where the B is on the second position, right? It's fixed there. Then we do the same analysis where in now this position, since I have removed the B from 21, we have 20 choices. At this place, 20 choices, because repetitions are allowed. Then the 99, the sum. So this is the situation, right? This is another possible arrangement. We can have another arrangement where B is occupying the last position for the letters, right? So these two, after removing the B from 21 letters, I'm left with 20. Repetition are allowed, then it's 20 and 20. Then the numbers are positioned as you can see. So these are the 3 possible arrangements that we can come up with, right? But as you can see, for each arrangement, I think the ways we can arrange is simply one and the same thing. Although obviously, at first we are saying 1 times 20 times 20 times 9 times 9 times 9. Then you say 20 times 1 times 20 and so on. Remember that multiplication is commutative. Commutative in the sense that 2 times 3 will give you the same answer as 3 times 2. That is the commutative kind of thing I'm referring to here. So this answer is the same as this answer is the same as this answer. They are the same, right? So the fact that we are saying this arrangement or this arrangement or this arrangement, we are supposed to add the first arrangement plus the second plus the third. This is how it is. And the multiplication of 1 times 20 times 20 times 9 times 9 times 9 is because of the fundamental counting principle. So this is first possible arrangement, second possible arrangement, third possible arrangement, but they give the same result. We know that repeated addition of the same number can be converted to a multiplication by counting how many times you are adding the same number. So here we are adding it 3 times, so it is the same as 3 times the same number we are adding, which is this one, and this reduces to this figure. So this is how we are supposed to come up with the favorable outcomes as far as the condition that we are given, exactly 1B. So once the B is used, it cannot appear anywhere, right? So now that we have that, then we can calculate the probability of a password having exactly 1B, which is the number of favorable outcomes over the number of possible outcomes. And favorable is this figure, possible is the one we have here, then it reduces to this. So this is how we are supposed to approach this problem. Now, let us go on to C. Calculate the probability that a password chosen at random has at least 1 4. Right, we are talking of at least 1 4, right? So we want to find the favorable outcomes, right? Which we are going to call set F. But I'm not going to use the approach of coming up with a column and some position. I'm going to use the idea of two sets being mutually exclusive and exhaustive. That is to say, I'm referring to the number of elements in the sets F and F complement. That means the number of elements in F plus the number of elements not in F will give me the sample space. Right, in this Venn diagram, I'm trying to present this situation. This is the sample space. This is the set F with elements, at least a 4 is present in the password that we are going to have, right? Then outside, we are having those passwords without a 4. So that if we add those password with no 4 plus password with the 4, we get the sample space, which is this one, right? So if that is the case, then our main focus is we want this set. So that means for me to know the number of elements in set F, if I know those in the sample space and remove the number of elements in the complement of F, then I'll get this one. So in this case, I'm going to make F subject, number of elements in F subject to the formula. That is, number of elements in set F is equals to number of elements in the sample space minus number of elements in F complement, right? Then if this is what gives us the number of elements in our favorable set, then all what it means, I need to find what is this, because this one I already have it, it's here. But what is the number of elements in the complement of F? That is, we want the number of ways we can come up with words with no 4. Then if that is the case, then it becomes simpler in the sense that we are simply saying outcomes without 4. That means from the 9 digits, I'm going to remove the 4, right? Then I'll remain with 8 digits. If I arrange them, that means the first 3 positions for the letters, since repetitions are allowed, I have 21, 21, 21. Now I'm using the 8 digits because the 4 is no longer there. So it will be 8, 8, 8. This is what I have here. So now using the fundamental counting principle, I multiply the 21, 21, 21, 8, 8, 8 to get the actual number of elements in the F complement. I can still work with this without actually getting the number. So now I substitute in this number of elements in F, which is this is equals to this is represented by that, which is this minus this, which is this, and the number we get is this. So we are saying the password with at least a 4 is represented by this. And this is the approach that I've used to get to the answer by knowing that 2 sets, that is a set and its complement, right? if they are mutually exclusive, and obviously they are mutually exclusive and exhaustive, because when you say what is in F plus what is not in F, then you should get the what? The universal set, right? That is true. Therefore, once I have done that, all what I need now is to find the probability of a password with at least 1 4, which is the number of favorable outcomes over the number of possible outcomes. Favorable is this over the possible, which is this. It reduces to that. Right. Here I've used the approach of the two sets being mutually exclusive and exhaustive. And the way the exhaustive is simply say if we add the elements of F plus those not in F, we get the sample space. That is, the two sets are exhaustive. Mutually exclusive, that means they don't have an intersection. What is in F has nothing to do with what is outside the F. So they are mutually exclusive. Now I wanted to use the idea of the two sets, the F and F complement, being complementary, right? In terms of the probability. So as an alternative method, I'm simply saying, let us use the probability rule of complementary events. That is probability of F plus probability of what is not in F should give us 1. And you can understand this by, if this is true, that means if I divide both sides of the equal sign by the number of elements in set F, here I'll get 1. Here I'll get the probability of F complement. Here I'll get the probability of F, because it will be number of elements in set F prime over the number of elements in the sample space. Here, number of elements in F over number of elements in the sample space. And it is a fraction, and it is the probability of the sets in question, which is what I have here, right? So if this is the case, or what it means, the fact that I want the probability of the set with the password with at least 1 4, that is, this is the probability that I want. Then I have to make this subject of the formula by taking this to subtract it to 1. And I'm talking of probability, which is different. Here I was talking of just number of elements, right? So as such, once I do that, the probability of F happening is equals to 1 minus the probability of the complement of F, right? The complement of F, that means we have already said the number of elements in the complement is represented by this, right? So over what is now the probability of it to be this over the sample space, which is what I have here. And remember, I'm talking of probability. That's the probability, which is this one, right? Then when you simplify, you realize that you come back to the same answer. So here, it's a question of using the concept of mutually exclusive and exhaustive in terms of the number of elements in the set of F and its complement and the universal set. Then you can also use the probability rule of complementary events. We simply say the probability of a set F plus the probability of its complement will give you 1. This is all what it takes, and it's nice that you should also get used to solve problems, trying to use the mutually exclusive and exhaustive concept and the probability rule of complementary events. I think with this, I stop here.